The water barely covers the rails. You can almost see the steel underneath it, and yet a freight train weighing thousands of tons sits completely still on the other side. To someone watching from the roadside, it looks ridiculous. A few inches of water shouldn't be enough to stop a machine that powerful. The train has massive diesel engines, steel wheels, thousands of tons of weight. So why doesn't the engineer simply keep going? Here's the strange part. The water itself may not be the thing the locomotive is afraid of. Underneath that enormous machine are electric motors working directly at the wheels. They need something that seems completely harmless during normal operation: air. Air to cool them, but those same openings that let air in can also let floodwater in. And beneath the train, something even harder to see may already be happening. Moving water can quietly wash away the ground supporting the tracks, leaving the rails looking perfectly normal while the foundation beneath them is disappearing. So the next time you see a train stopped in front of what looks like a shallow puddle, don't ask why such a powerful machine is afraid of a little water. Ask a different question. What can a few inches of water do to a train that you can't see? Let's get into it right here on Small Things. Not the diesel engine turning the wheels. Here's something most people quietly assume without ever really checking it. In a diesel locomotive, the diesel engine does not turn the wheels. Not directly, not through gears, not through a drive shaft connecting the two. None of it works that way at all. The diesel engine's actual job is generating electricity instead. It spins a generator, the generator produces current, and that current gets sent to electric motors mounted right at the wheels themselves. Those motors, not the diesel engine itself, are what actually pull the entire train down the track. The whole arrangement has a name: diesel-electric transmission. It sounds like a minor technicality, the kind of detail only an engineer would care about. It's actually the entire reason a few inches of water can end up mattering at all. Why anyone built it this way? It did not begin as a strange workaround someone stumbled into by accident. It began with a much older, more basic engineering problem. How do you transmit an enormous amount of power reliably from one engine to wheels that need to turn at wildly different speeds depending on whether the train is starting from a dead stop or already running at speed? A car solves that particular problem with a mechanical gearbox, clutches and gears shifting together to match engine speed to wheel speed. Scale that same idea up to a locomotive engine producing thousands of horsepower, enough to start tens of thousands of tons of freight rolling from a standstill, and a mechanical gearbox capable of handling that kind of force would need to be enormous. Gears built that large, strong enough to survive that kind of torque without shattering under load, would be heavy almost beyond reason, expensive to manufacture in the first place, and prone to failing under the exact repeated stress a freight locomotive experiences every single day of its working life. Electricity solved the same problem in a completely different way. A generator can produce usable current across almost any speed the diesel engine happens to be running at, and electric motors can deliver enormous torque from a complete standstill without needing a single physical gear to shift at all. No massive mechanical transmission required anywhere in the design, just wires, a generator, and motors built directly into the wheel assemblies themselves at each axle. Engineers worked this exact arrangement out more than a century ago in the earliest years of diesel railroading, and it solved the underlying mechanical problem so completely that it remains the standard approach today, updated considerably in its details but identical in its basic underlying logic. That solution came with something built permanently into it, though, a consequence nobody was specifically trying to create when they solved the original mechanical problem. Putting electric motors at the wheels meant putting electric motors right down near the rails themselves, close to the ground, close to exactly where water eventually goes when it has nowhere else to flow during a storm. It wasn't a design flaw exactly. It was simply where the solution to one problem happened to physically sit, and nobody a century ago was designing specifically around floods hundreds of miles away, in places the rail line hadn't even reached yet. Where the water actually gets in. So what actually happens when water reaches a component built for that job? An electric traction motor pulling a loaded freight train up a grade works hard, and working hard generates real heat, considerably more than a small motor idling under light load. Left with nowhere for that heat to escape, the motor's internal windings would simply overheat, and overheated windings fail. So every traction motor relies on constant airflow, air pulled in, pushed through the casing, and vented back out to keep the internal temperature within a safe range while the motor works. That need for constant airflow creates an unavoidable trade-off, one that can't really be engineered away without creating a worse problem in its place. A sealed, fully watertight motor would solve the water problem almost instantly. It would also trap all that heat inside with nowhere at all to go, and the motor would overheat and fail considerably faster from trapped heat than it ever would from occasional water exposure during a flood. Sealing the problem away isn't really a workable option then. The airflow has to stay open for the motor to survive its own operation, which means the motor has to stay at least partially open too, to the exact same air that eventually carries water in during a flood. And that's exactly where the real danger lives. Inside the motor, copper windings are wrapped in insulation designed to keep electricity flowing only where it's supposed to flow. That insulation is built to handle heat, vibration, and ordinary humidity without much trouble. What it isn't built to handle is standing water working its way in through the same openings meant for cooling air. Once water reaches those windings, it can create a path for current to travel somewhere it was never supposed to go, arcing across gaps the insulation used to block. The result is usually a short circuit inside the motor itself, sometimes an outright electrical fire in more severe cases. And either way, a motor that stops being usable until it's pulled apart, inspected, and rebuilt from the inside out. It's not the water you can see. It's tempting to picture any water touching a train as an immediate, guaranteed disaster, the kind of framing that makes for a dramatic headline but doesn't really hold up under scrutiny. That's not accurate. Whether floodwater actually threatens a locomotive depends heavily on depth, on how long the crossing actually takes, on the specific motor design involved, and on conditions that change meaningfully from one flooded crossing to the next. A light film of water sitting across the rails isn't remotely the same situation as water rising well above the axle. Crews and dispatchers weigh exactly that kind of judgment call carefully, rather than treating every single wet rail as an automatic emergency requiring a full stop. There's a second danger, though, one that has nothing to do with the locomotive itself, and it's genuinely easy to miss entirely because it's invisible from the cab window. Moving floodwater doesn't just sit quietly on top of the track. It can push underneath it instead, washing away the crushed stone ballast that holds the rails and the wooden or concrete ties firmly in place. A rail can look perfectly straight and properly aligned from above, exactly the way it's always supposed to look on an ordinary, uneventful day, while the ground actually supporting it underneath has already been quietly hollowed out by the moving current. Nothing about that would be visible just by looking down the line from the cab. It's a hidden structural risk sitting directly beneath a track that still appears completely normal to anyone looking at it. Judged on sight, not by a chart. A track inspector arrives at a flooded crossing hours after the water has already receded, probing the ballast with a metal rod every few feet along the rail, checking for the soft, hollowed-out give underneath That would mean the current had been quietly working under the ties long before anyone upstream even noticed the water rising. A dispatcher sitting miles away in a quiet, dimly lit office watches river gauge readings climb steadily through the night, coordinating by radio with a crew still several hours away from reaching that exact same flooded stretch of track sometime early the following morning. A freight train crossing an entirely dry section of rail runs at noticeably reduced speed anyway that particular afternoon, simply because heavy rain earlier that same day had already lowered the margin for safe braking, regardless of whether any standing water happens to be visible along that specific stretch of track. A shop crew lifts a locomotive carefully off its wheels weeks after an otherwise unremarkable flooded crossing earlier that season, pulling a traction motor that finally failed quietly during a routine inspection, the actual damage from that earlier water crossing only becoming fully visible long after the original trip itself was over, and everyone involved had already forgotten about it entirely. Strength with conditions attached. A locomotive doesn't stop in front of floodwater simply because it's fragile or weak. It stops because the enormous strength built into that machine depends on a handful of specific conditions being quietly met, underneath everything else that's happening in the moment. The traction motors need airflow to survive their own heat, which means they can never be fully sealed against the water sitting just a few inches beneath them. The rail underneath the wheels needs solid ground to actually support it, and moving water can hollow that ground out without leaving any visible sign above the surface. The water you can see might only be a few inches deep. The danger that actually matters might be sitting inside the locomotive or hidden entirely beneath the rails themselves. Sometimes the safest thing a powerful machine can do is simply stop and wait. If this changed the way you look at a train stopped before a flooded crossing the next time you see one, let us know in the comments below what you want us to explore next in a future video. We might make it our next episode. Thanks for watching. History often hides in the smallest details.